All right, so we're jumping into this next one. Now, this is linear transformations for matrices. So I was just going to bring up that previously we've looked at functions. So functions is something you learn pretty early on. And the idea is that you represent a function with this input value. And whatever you put in here comes out here. So if we put a 1 in here, it is squared and then it has 3 added to it. That's what a function is. Now, we can actually transfer this to matrices. So here, we're looking at, I've written 2 matrices out, U and V, and we've got this function here, this T function. So if I was to put T in here, so not T, if I was to put U in this matrix, what I would be doing is I'd be going, well, my input here is T and U was 1 and 3. And then I'm applying that into this function here. So it says 2 times x, which means that my top thing here is going to be 2. And then it's 2 times whatever's in this x input bit, this top bit. Okay, so looking in here, that is a 1. So we have 2 times 1. And then my next one is 3 times y, whatever my y is. So y is this bottom value here. So I put that 3 in there, and then minus x, so I have minus 1. And so this means that this function maps, so 2 and then 9 minus 1 gives me 8. So it means that this thing here, my u, once it goes through this function of t, so it's like this t value here, this u value becomes, so the u originally becomes, I'm trying not to get too crazy with the notation because this course doesn't actually use it. This is almost the hardest bit here. So I've done the wrong one. So what it's saying is that if we have this 1 and 3 input, we put it through this linear transformation and it comes out as a 2 and an 8. Okay, and so we end up pretty much this is transformation. So it's just the word for this transformation is literally function. We've done it lately. So let's jump down to some definitions. So a vector-related function t, so that we've done t up here, is a linear transformation if. So these are the definitions for if it is. So it's a linear transformation if we put 2 matrices added together in the function and it equals the 2 matrices put in the function by themselves then added together. The other one, that's the addition property, and the other one is if we multiply our matrix by a scalar constant, then put it in the function, it should still come out as the same thing multiplied by the scalar constant. So, all right, that's it. And then there's some properties of linear transformation. So if t is a linear transformation, then t, if we put the 0 matrix in, we get the 0 matrix out. Obviously here, if we have a negative function, we can just move the negative out the front. And then this one here is a combination of these two. It's just saying that we can keep adding. If we have lots of these, a scalar plus a matrix and lots of these together, we can break them out individually. So let's actually apply this. So we've got to show this first one that this t is a linear transformation. So what we do is we get a general matrix. So we're just going to go U, okay, and U is our matrix, and we'll just go x1, y1. Now I've just picked the subscript 1 because it's the first matrix we've done. This one here, we'll go x2, y2. Now, previously we've done A's and stuff like that. The reason we've done X and Y here is it's going to make it easier to input into this thing here. So our first rule was that if we do T U plus V, it should equal T, this should equal T U plus T V. Now, I'm just going to move that down because that's our aim. We don't want to have it in our proof just yet. So we've got T U plus V, which means we're going to have T, and we've got in here x1 plus x2 over y1 plus y2. Okay, so this is my u plus v. If I put them in there, these are in this function here. And this equals t. I don't need the t anymore, sorry. Let's get rid of that. So it now equals y was y1 plus y2. Okay, and then x plus y, so our x value is x1 plus x2 plus y1 plus y2. So now we're gonna, this thing here, if we equal this, and now I'm just gonna pull it apart a little bit, and I'm gonna rearrange these values here to have the ones together. Because realistically, I can rewrite this as y1, I'm just going to go plus and y2. And then this bottom line here, I can write this as x1 plus y1 plus x2 plus y2. And if you're looking at this here, well, this is pretty clear that we can, because of the way we add matrices, these pluses in the middle, we can write this as two separate matrices as y1 x1 plus y1 plus y2 x2 plus y2. And now looking at that, we're looking at, this conveniently is u. This value here is tu. Maybe I should move that down. Not quite enough room here, is there? Let's just drag that right down, and I'll just move this just into the space. So this here is, if I'd put u just originally into the function, if I'd put this in here, I would have got y1, x1, y1, which we've got here, and then we've got the same thing for v. So perfect, this works. So now we're going to prove our other rule, which is TKU has to equal KTU for it to be linear. So what we'll do is we'll drag this again. So when you do a proof, we only do it one-sided. So this means that we're looking at T, and we've got KX1, KY1, okay? And we put this in our function and we get, this means we get KY1, and then we get on the bottom KX1 plus KY1, okay? Now this whole thing, I can pull my K values out because everything has a K here, so K is a common factor at the top. And the bottom, I'll pull them all out. K, Y1, X1, Y1, so plus in there. And you'll notice that this now equals KTU. Okay. Oh, and now I've got ahead of myself because I hadn't done the next one. So, no, let's just quickly write it in. So we've got this next one is show by counterexample that T x y is equal to x over y squared is not a linear transformation. So in this particular one, we're just looking to prove our rule. And so they've done it by picking numbers in here. So realistically, we could do that, or we could do it as a general form, just like we did before. So either or works, but let's actually do it as a general form because you can look at that example. So let's just do u equals x1, y1, and v equals x2, y2. So if we're going to do this as a counterexample, we remember that we're looking at tu plus v equals tu plus tv. Now this would mean I'm going to drag that down because that's what we're aiming for. So this means that we'd be looking at t x1 plus x2 over y1 plus y2. Okay, now, if you look at their example, they picked one of these was just 1, and the reason they've done that is it makes it a lot simpler. But we're looking here at, when we put this in our function, we're going to get, we just get our x values back out. So this is going to mean we're going to get x1 plus x2. But then our bottom one here is squared. So that means we're going to end up with y1 plus y2 all squared, which means we get here, we're going to get x1 plus x2. So that's good. That bit at the top, you can already see it looking linear. But this bottom one here is going to be, and I'm probably going to need more room to do it, we're going to be looking at y1 squared plus 2y1 y2 plus y2 squared. Okay? Now, straight off the bat, this is an issue because you know if we put these values in, we would get, I'm just going to write this step here. If I put these values in, I can tell you right now, this matrix is meant to look like, it should look like x1, and then it'd be y1 squared plus x2 over y2 squared. Now you can see from this here that we've got this term, we've got this term, we've got this term, we've got this term. So these terms are all here. But this, unfortunately, means that this cannot equal TU plus TV. Therefore, T is not a linear transformation. Okay, so in this, that means now that the moment we counter one of these two rules doesn't work, it still can be a transformation. It's just not a linear one anymore. All right, I'm going to leave it there. Have a jump into these yourself. Try and prove these with the properties. Just remember that you're looking at, you're treating this like a function. So make sure this input here or this top element here, these aren't fractions. Go in and follow the function notation. Thanks, guys.